In section 10.1, we look at whether or not a sample could come from a population with a known or expected population mean. In this case, the example comes from the field of botany. An experiment was done to test the conduction of celery xylem, where the celery xylem was dipped, the stem was dipped into dyed solution. The leaves were left on top of the celery stalks to see if the leaves would improve the rate of conduction up inside the celery. From a previous year, data was known on what the conduction rate for celery with no leaves was. And so we have a new sample this year of celery conduction, celery with leaves, and we're going to see whether or not the celery with leaves is conducting better than the celery conduction last year when there were no leaves used. So it's a comparison to a known and expected population mean. So to do this, here's our data. In column A are the flow rates for this year from 7 different experiments with 7 different stalks of celery that were used. You can see them here from A2 to A8. So starting off here, our sample size is the count of A to A. The sample mean is the average of A to A. You can see that in there. This is the standard deviation, STDEV. And here is the standard error, chapter 8.2. To get the T critical, ignore the 0.95. Yes, we're using a 95% confidence interval, but that's not how to do this function. We're going to use a function called the T inverse function to calculate the critical values that we need to determine the lower and upper bound of the 95% confidence interval. And we're going to use 0.05 right here. That will be the number we always use in this course. That leaves us with a 5% chance of what we will later learn to call a type 1 error. We always in this course use 0.05. It's sort of the golden standard for confidence interval calculations. Why is it 0.05? Because that's what happens when with the leftover of 95%. And we'll hit this a little bit more heavily in section 10.2 and 10.3. It's the tail area beyond 95%. And then the rest of the T critical is simply the sample size minus 1. Always the sample size, always minus 1. And if you press check, in most cases you should see a number larger than 2. In this course you should see a number larger than 2. It cannot go below 1.96. Cannot. Not in this course. And not in most cases that any two-tailed test with a 5% type 1 error, a 95% confidence interval, it's always going to be above 1.96, above 2. If you don't see a number above 2, something went wrong. So this sample comes from a population which has a population mean somewhere between the lower bound and upper bound. This is chapter 9.2 stuff. All I have to do is calculate that. I say equals the mean, and all I have to do is tap on the mean. It's already available to me. Minus, this is the lower bound, T critical, the number I just calculated, times the standard error back here. It's telling me how many standard errors I have to go to have a 95% probability that I've included the population mean for this sample of 7 celery stalks. The lower bound is 1.13. The upper bound, similar calculation, equals the mean. I like to tap these in. Plus T critical times the standard error. There's the asterisk for the times as usual. Check. I have a confidence interval from 1.1338 to 1.5718, 1.572. These 7 celery stalks come from a population whose population mean is somewhere between 1.13 and 1.57. Last year, the known population mean flow rate for the celery with no leaves was 0.8. 0.8 is not between 1.3 and 1.57. We can look at that if we jump over here and a number line. The number line here, and I'll enlarge this some, bring it out. This lower end is 1.13. The upper end is 1.57. The orange line are the places the population mean could be for this year's celery with leaves experiment. Last year, the population mean was down at 0.8, back here. That's not a possible population mean for this sample. This sample can't go that low. So we can reject the possibility that celery with leaves has a flow rate way down at 0.8. In other words, the leaves on the celery drive the flow rate. And indeed, that was a note made in the laboratory itself, was that the laboratory failed last year. Last year was a fail because last year we cut the leaves off and the celery did not conduct dye up the xylem. By leaving the leaves on, we got much higher rates of flow than we saw last year, and we can rule out the possibility that it could possibly be as low as 0.8. No way this could be as low as 0.8. So in the very next section, we're going to be talking about, we're going to reject the hypothesis, the null hypothesis that this thing could be 0.8. It's not. But in this chapter, we simply say the confidence interval does not include the population mean. The population mean is not a possible value. Yes, this is significantly different. And that's really 10.1 in a nutshell. It's looking at the data you've got, usually a sample, and checking to see whether it could be some other previously known or expected value. Be careful with this function. Always put 0.05. That's 5% for you mathematicians. That's 5%. In this course, we always use a critical value running off a 5% chance of what we will later learn to call a type 1 error. This 0.05, will also have the name alpha. It'll also get the name alpha, which is just a letter we use for a type 1 error in statistics. It's a Greek letter A. So be careful with this t-critical function. Always make sure it's bigger than 2. As always, thanks for watching.